Hello everyone, welcome to next in the series of Postgres webinars. My name is Liaquat and I am the Digital Marketing and Communications Manager at Second Quadrant. Today we will be covering key concepts of Postgres vacuum and auto vacuum. And to talk on that, we have with us Tom Kincaid, who is the General Manager North America at Second Quadrant. Without taking more time, I'll switch the controls over to Tom. Tom, please go ahead.
Okay. All right. Thank you very much, Liquad. Once again, my name is Tom Kincaid, and I've been around the Postgres community for about 10 years or so. And I'm going to take you through something that's sort of near and dear to my heart, as I've had to talk about it quite a bit. So let's start before I get too into things, I first want to introduce Second Quadrant. So Second Quadrant was founded by an enterprise architect, enterprise developer who works on many different databases and became very engaged with Postgres, and he founded a company called Second Quadrant, as Simon Riggs founded 15 years ago, really about contributing to Postgres and supporting and doing consulting and training around Postgres. So some things he started were backup and recovery, point-in-time recovery. These are things Second Quadrant has contributed over years to the Postgres open source project. And string replication, logical replication, stored procedures, was something with transactional control, something we contributed recently, and a number of performance improvements for partitioning. And we're funded entirely by the support, not entirely, but mostly by the support of Postgres servers that you run in your enterprise. And so if you are considering support for a large production Postgres deployment, we would very much like to work with you and be involved in you. And we wrote the code for Postgres. We also wrote a number of books that you can, we do Postgres and for the most part, nothing else. Okay, so why did I decide to write this talk? I wanted to give a little bit of background about it and explain why. I've spent a lot of time talking to very smart people about vacuum. These are Postgres internals developers, what you would consider to be committers on the project. And then I've also spent years talking to customers who are confused about vacuum. You know, what does it do? How does it work? And then I've also spent years talking to customers who are in pain. And a lot of times they're in pain and they have to go back to this fundamental understanding about vacuum and what it is and how it operates. And there's this understanding they need to gather. You know, all they know is I'm in pain because some element of vacuum is occurring in my database. And I really felt I needed pictures to explain it. And generally speaking, I feel there just aren't enough pictures in the Postgres community and the documentation and around things. There's various things going on. So I wanted one thing, it's a community, we all contribute in our way. And one thing way I thought I could contribute is by drawing some pictures about this and some other things that are hard for people to understand. And so that's my thinking here, and that's what I'm going to be taking you through over the next little bit here. Okay, so the first thing is I wanted to kind of have some general best practices around vacuum. The first thing that you need to do if you're going to deploy a Postgres database, particularly a large Postgres database, or one that could become large, is you need to understand what vacuum is and why it's necessary. That's the first thing, understand. And then based on your understanding, you want to make some design decisions around your database. And then also you want to monitor vacuum, and there's various ways of doing it. As part of any Postgres deployment, you do monitoring for things like disk usage, CPU usage, and a variety of other things. But ultimately, you need to monitor for vacuum as well. All right, and there's various things that can help you do this. You can use tools like Zabbix. There's a set of canned queries you can find in the Postgres community that Second Quadrant has. It'll give you, and there are a variety of extensions such as pgstat tuple. So once you have this first set of things, once you have your understanding, once you have your design and your monitoring, based on the results of your monitoring, you're going to tune the vacuum. And I think this is actually quite interesting. A lot of times people start in the other direction. They're having pain with vacuum, and then they start tuning, and then they start monitoring, then they realize they need a different design, and they need to up their understanding. So it actually sometimes you want this to go from the, these steps to occur from the top to bottom. Unfortunately, they often occur in the other direction because of some particular issue. Okay, so let's talk about, we're going to talk a little bit about why vacuum is necessary. I'm going to talk a bit about what it does. And then I'm going to actually spend a lot of time talking about how it does, what it does, so that you can have in-depth understanding. And then finally, I'm going to talk about what your options are for tuning it, and then we'll go into some best practices. So without any further ado, let's get started. Actually, before I start, there are a few things I want to mention that I'm going to talk about in future talks. I'm hoping that you can come back for it. So one thing that's frequently tied up with vacuum is a process called freezing. And I'm not going to talk about that today because in order for me to talk about that, you need to understand what the concepts that are in this presentation. That will be a future webinar I will do. So we're going to do vacuuming through pictures today, and we'll do freezing through pictures in the future. And then we'll also talk about something called hot heat, and that'll also be hot stands for heap-only tuples or hot updates, and fill factor through pictures. So there are going to be some, I guess there's going to be one more advanced, I'll call it, maybe I should title that advanced vacuuming through pictures. And then finally, we'll also talk about monitoring in a future talk. All right, so there we are. We'll get started now. So we're going to even go a little bit before we get into the vacuum process. We want to get into some Postgres internals basic. Postgres reside on disk is 1 GB file. Okay, at Postgres table, you can actually go on disk and you can find the 1 GB files that make up the database. And then each file in a typical Postgres deployment consists of an 8K page. And we interchangeably use the terms pages and blocks. And the page is the unit of transfer from disk to memory. And the area of memory where it goes into is frequently referred to as shared buffers. So we have our first picture. So kind of laying this out, Postgres is laid out as a number of, a table is laid out as a number of files. So this might be a 3 GB table, and it would have 3 1 GB files. Each file is broken up into 8K blocks. And then what happens is there's what's called a buffer cache. And on a large server, this usually is between 8 GB and 64 GB. It can vary quite a bit depending on your deployment. And there's various rules as it should be a certain percentage of RAM based on various rules that we have. So the first thing that happens is when I read a page, it's brought into the buffer cache. So it's transferred from the buffer cache gets populated with pages as they're transferred to and from the file. And then, and then the database operates on these pages, all right? So pretty simple database type algorithm, all right? You know, I'm transferring files from disk and into memory, okay? And the unit of transfer is an 8K block. Now, Postgres, like many other relational database, is an MVCC database, multi-version concurrency control. So there's the first term, okay? And the concept of this is that for a single row of data, there can be one writer and multiple readers, okay? So one transaction can be updating the row while many other transactions are reading the row. MVCC, multi-version concurrency control. So I'm going to start with a very simple example here. This is the PG Bench database, and it has the following items in it. It has an account ID, a balance, and it has account ID, a balance, and a branch ID and a balance. Okay, so effectively 3 columns, or 3 tables. Account this is the PG Bench accounts, which has 3 columns. All right, so that's what we're looking at here. It has the account ID, the branch ID, and the balance. So that's what we're working with. So we'll start out here. This is Tom's account. His account ID is 3, his branch ID is 1, his balance is 500. A transaction starts at time 1. Okay. And then it does a begin. Then another transaction starts at time 2, and transaction 1 continues. While transaction 1 is executing, transaction 2 updates Tom's balance to $1,000. So a new row is created in the database. So important concept, it didn't change the existing row, it created a new row. So there's where the multiple version comes in. Transaction 2 now commits. So here is the question. Back in transaction 1, after transaction 2 is committed, what should the balance be? What should the selected balance be from the database? If I select the balance, effectively Tom's balance, where AID is 3, what should you see? And the answer is it depends. And if this were a live presentation, I would, well, we'll see if something comes in here. If this were a live presentation, I would ask the audience, what should the answer be? And we'll see if we have any questions here, any answers here. So I'll just wait a moment, but I'm not sure if we're set up to do that, to ask questions and answers. But anyhow, so therefore, let me go ahead and answer it. Well, the answer is it depends. And what it depends on is what you have the transaction isolation level set to. So depending on the transaction isolation level, the answer will vary. If you have it in various levels, what you would see in this case would be the value of 500. In other cases, you would see a value of 1,000. So the point is that the rows need to be, the old row needs to be kept around. This value of the row needs to be kept around because there are other transactions that may need that value of the row, depending on the transaction isolation level. And that is the way Postgres implements multi-version concurrency control. And the important thing to understand here, other database implementations implement multi-version concurrency control by putting these old tuples into what's called an undo log. In the case of Postgres, they're kept in line in the same database. And that has advantages and optimizations, but it also, with every advantage comes a trade-off. And the trade-off is, over time, I get dead tuples. Okay, so this tuple is dead, meaning there are no transactions, executing transactions that would access this tuple when during the course of their execution. All right, so all the transactions that were in a case like transaction 1 where they need access to this particular tuple have now committed in one form or another. So now you have what's a dead row within the database. All right. And then you have the live tuple. So you have the dead tuple and the corresponding live tuple. So this is the situation that develops, and this is where some of the people will periodically run into pain. Is I do an update, in this case, my very simple update. Okay, and there's my schema down here. Then I start doing my very aggressive updates, and I get a situation like this, where the gray represents the live tuples. I have a lot of dead tuples in relation to how many live tuples I have. So as time goes on, if I don't have my vacuum settings tuned properly, which a lot of people don't, things get bad and my performance drops off a cliff. And to kind of explain why that is, let me just go one step further. It's not just the tables, it's the indexes. So not only do the tables get bloated, but the corresponding indexes on the table also become bloated. And you can see in this particular index, there are entries for dead tuples and there are entries for live tuples. And so over time, a couple of things happen. The database starts to occupy more disks. And remember I talked about shared buffers. You actually find less data in the cache. And eventually you need to pay a huge price for vacuum. And so vacuum is effectively reclaiming the space of these dead tuples. And I'll get into specifically how that happens in a moment. But think of vacuum this way. You could pay a little frequently or pay a lot later. All right, so you can pay your mortgage once a week, or you can pay it once a year, in which case you'll have different levels of pain with that particular payment. And so one phrase I've heard in the past is if you're having problems with vacuum, you need to do more of it. All right, so just to kind of get that, why is excessive bloat a problem? I've mentioned that you're occupying a lot more disk, but if I do this, if I execute this particular query where I select star from PG bench accounts, the question is, am I going to access one page from disk, 4 pages, or 400 pages? And as you can imagine, accessing one page is significantly faster than accessing 400 pages. So there is your fundamental issue there. Okay. Okay. So now we've talked a little bit about how this happens at the application level. I'm going to dive down now into Postgres internals just a little bit. And I apologize. I know this is not always the level of detail that everybody wants, but unfortunately, it's something as if you ever get into a tuning situation around vacuum, something you need to understand. What you're looking at here is a Postgres page. All right, so you have a page header, you have a page with 2 item IDs, you have a row header. All right, and this is effectively how it works, is that every item ID is, I forgot how many bytes it is, but it's a fixed number of bytes, refers to a row ID. So an index will refer to the item ID, which in turn will actually refer to the particular row on this 8K page. All right, so item ID to order ID. Okay, so that's fundamentally how it works. And the item IDs grow from the top of the page towards the middle of the page, and the actual row data grows from the bottom of the page towards the middle of the page. All right, so that's there's a few more details and a few more items on the page, but that's fundamentally how it works. So if I update my balance to equal 1000, where the ID is 3, what actually happens is this. I create a new item ID, a new entry in the index, which creates a new item ID. All right, so that's the first thing that happens is a new entry gets created on the page. And then a new item ID also gets created on the page. All right, so there's the new item ID. And then the new row gets created, so I've updated the balance. And here's the important thing that happens is that the old row now has a pointer to the new row. All right, so the event that the old data is accessed in some scenarios, it will actually forward it on to the get the data from the new row. All right, so that is how things go, and that's sort of, and then over time, these pages, this is what it will look like, is that the page starts to become bloated. You get these dead tuples, and then you have these dead item pointers on the page. So that's effectively bloat. And the page, and then ultimately what's happening is the page can take fewer and fewer rows, and the rows need to be, new entries need to be put on different pages. So vacuum's a 3-step process, all right? And this is, the reason I explain this is a lot of times when you're looking at debug messages of vacuum, it'll tell you which step it's in. And so sometimes it's important to see where you're at. So the process is you scan the tables to identify the rows and item IDs that can be reclaimed. And what you do is you place the item IDs in a data structure called maintenance workmem. And actually the data structure is not called maintenance workmem. Workmem is the setting of the value that controls the buffer for. And then you mark the rows spaces as reusable. You reorganize the pages. This is what's happening in step 1. So these are 4 sub-steps of step 1. And then in some cases, you return the space to the operating system. So if there's a page at the end of the table that has no items on it, it'll return it to the operating system. And then you scan the indexes to remove all the item IDs of the dead rows. And then after scanning indexes, mark the item IDs as reusable in the table. So we're going to draw this out. Okay, so here is a page, here's a table with consisting of 4 blocks. Okay, and so phase 1, we scan a table's heap to identify the dead tuples and then place the item IDs in maintenance workmem. All right, so we're scanning that. Okay, and then we reorganize the pages. So looking here, you'll notice, if you look at block 1 or page 1, what actually happens are 2 things. you'll notice there's no more dead tuples at the end of the page. And then, but there are still these dead item pointers at the top of the page. All right, so we're still in phase 1. The reason you'll notice that block 3 has some additional dead tuples on it is that there's potentially a transaction open that needs these tuples. All right, so there you go. So now the next phase is we scan maintenance work mem, and we're looking to claim the dead tuples from the index scan. So we found all the dead tuples here in phase 1. Okay, now we are, I'm sorry, just to kind of be a little more clear. We've put all the dead item pointers in maintenance work mem in phase 1. And now we're going to scan the indexes with the values we collected in maintenance work mem and start what I would call cleaning those up. And this is what the index will look like after the vacuum phase. So you can see that now these spaces are available for reuse by future inserts or updates. All right, so that becomes, so we haven't compressed anything, but we've made things available for reuse. All right, now the last step is we need to go back and mark the item pointers for free reuse. So we've made sure that no more indexes point to these item pointers. So now we make the item pointers on the page reusable, and that's what you're seeing here. All right, so these item pointers are now reusable for future updates and inserts. And again, page 3, I'm leaving that there because there are potentially some open transactions for this particular page. All right, so that's what's happening there. Now, the next thing that we could talk about is something called vacuum full. If I run a vacuum full on a table or a database, that effectively is copying the table. So here's how it works. So I do a vacuum full. I take a full table lock. All right, so this is important, a very important concept. If you do a vacuum full, no other operations can happen on this table. So it's, and we've seen this happen on occasion where a database administrator says, oh my gosh, this table's really bloated, let's do a vacuum full on it. And then it's a production system and the database is locked and nobody can access it. And I've actually seen this happen where you have a bunch of triggers that on table A, which insert values, a shadow table, so if you're using some sort of logical replication system like Sloaney or Bricardo, and you vacuum the trigger tables or the shadow tables, all of a sudden the triggers can't fire on the main table. So the bottom line is, remember, vacuum full takes a full table lock. It effectively causes an outage on the table. If you do a vacuum full on a database, it potentially causes an outage on the database. So do it sparingly. The nice thing about it is it actually does return space to the operating system. So in this case, I've compressed 4 pages down into a single page. All right. So vacuum full, used sparingly, but can be very effective in certain scenarios. Okay, so now the a couple of things to know about a couple of sort of best practices around this. Okay, so one is the default maintenance work mem value is almost always too low. So at any real production server, raise this to a gigabyte. Always raise maintenance work mem to a gigabyte. It's worth doing. All right, and it does. You can raise it higher, but I believe I've been told in certain scenarios that actually doesn't produce the results you think. So top it off at about a gigabyte. One thing and people don't realize in Postgres is, people will say, okay, I'm going to index everything. That's the way I did it in this particular database. That way every query will run faster. Well, maybe or maybe not. If your indexes are unused, every time you do an insert or an update, they need to be updated. So there are many different update operations that occur. And then when you do a vacuum, it needs to scan all those indexes. So if I have a table with 50 columns, each one of them index, I got to scan each of those indexes. So find out if you're using those indexes. And there are a variety of queries for doing that. And if you're not using them, remove them. Now, one thing I will say, remove with caution. Removing an index is very easily drop index, but recreating it can take hours, in some cases days. So just keep that in mind. And then the next thing is to let vacuum operations finish. I can see somebody say, I've seen somebody say, look, this vacuum operation's been running for 36 hours. Should I let it finish? The answer is yes. You want to there's ways to monitor how long it is, because you're going to have to pay that penalty, and you're going to potentially have to endure that 36 hours all over again. And vacuum operations, because they are writing to disk in many occasions, do impact performance. So again, this is where the design and the tuning comes in. All right, so how do vacuum operations get run? When does it happen? Where does it happen? Okay, there are a couple of different ways. One is you can manually via the vacuum command. So you just say vacuum database or vacuum table, and it's good for defining. And typically it's done by cron jobs. I know nobody's on my system from 1 a.m. to 2 a.m. Every morning, so I'm going to vacuum my database then. And you can vacuum specific tables on the database. So maybe one particular table is particularly problematic, so you vacuum that one. The other thing you can do is by auto vacuum workers. So auto vacuum is when certain thresholds are crossed with respect to certain tables or the database, it will start vacuuming. And that really is the preferred way of doing things, is to let auto vacuum take care of vacuuming the database. So that's that's sort of the classic thing. So I'm going to tell you a little bit about how auto vacuum works, and this is where where some of the understanding comes in. There's actually a process in Postgres called the vacuum launcher process. And if you do a ps-ef kind of grep vacuum on a Postgres server, you will actually see the auto vacuum launcher process. Okay, follow me? I guess you can't say yes. That's looking for the interactive thing. And then what it does is, if certain thresholds are crossed, it will start a vacuum process, an auto vacuum process. So the first thing that happens is there's a value in the Postgres conf called nap time. So if nap time expires, typically it's 60 seconds. I think the default is 60 seconds, which is a reasonably good value for nap time. It checks to see if vacuum. And the next thing is how many worker processes are already running. So auto vacuum workers. So if nap time expires and max auto vacuum workers is not reached, meaning there are more than, typically I think the default is 3 auto vacuum workers. We generally don't see people go higher than 5 to 10. I would say typically around 5 is about as high as you want to go. So it's the value of max auto vacuum workers. Okay, then it launches an auto vacuum worker process. And the auto vacuum worker process will use the maintenance work mem, maintenance work mem area of memory, and it will start vacuuming one table at a time. It creates a plan as to which tables it's going to vacuum. Okay, let's say another nap time value goes by, another 60 seconds, another worker process is started. So you now have 2 vacuum workers working in parallel to vacuum the database. All right, in this case, one is working on the accounts table, the other is working on the tellers table. So far, so good. All right, so the question is now tuning this auto vacuum. There are a couple things that come into it. When should I start vacuuming a table? Okay, at what point, as the thresholds I mentioned earlier have been crossed? And how long do I let vacuum run before I pause for a little bit? And how long do I pause, right? So if vacuum runs continuously, it could really create a lot of problems. It could create IO spikes. It could starve other operations that you want to have happening in the database. Okay, so I'm going to take you through a little bit of code in the Postgres source code, and I'm going to go through a very specific example about how this works. All right, so this is some actual code from autovacuum.c. The threshold equals the vacuum base threshold plus the vacuum scale factor plus the rel tuples. So let's look at that a little bit. Okay, if I look at Postgres conf, what I'm looking at is the scale factor in this case is 0.2. And then my this is wrong. The threshold in which this should be vacuum and not analyze threshold. The vacuum threshold should be 5. And here is what I do. Okay, so I'm looking at this table over here. I actually have this example. I went through and I counted. There are 34 tuples in this table. There are 19 dead tuples in this table. If I take 5 and I say 0.2 times 34 and add 5, the vacuum threshold is 12. 12 is greater, 19 is the number of dead tuples, is greater than 12. So auto vacuum will run on this table. So it's the auto vacuum scale factor together with the auto vacuum threshold that determine if you should vacuum this table. All right, so now the next thing is throttling the vacuum. Auto vacuum will runs for a cost limit. All right, so the way the cost is it's determined as if, did I find this page that I'm vacuuming in cache, or did I find this page in from disk? The default auto vacuum cost limit is very low. So its default is 200, which means it will yield quite frequently. And how long will it yield for? It'll sleep for the auto vacuum cost delay. And the cost delay by default is 20 milliseconds. So I do some number of a little bit of work and then I sleep for 20 milliseconds. So the cost limit is how much work I do. The delay is how long I go before I do some more work. Okay. And then I continue on for another another period of time. All right. So a couple of things to go through here. Okay, you always want to enable auto vacuum in PostgreSQL.conf. If you don't, you do it at your peril. You really need to keep that. You configure the number of auto vacuum workers and by setting the auto vacuum max workers. So a few things about threshold. Remember to design first if you can. All right, and oftentimes it's too late. Okay, and generally a rule of thumb, you want to monitor how much bloat are you going to tolerate. The general rule of thumb is about 20% of the table should be bloat. If more of it is than that, or 20% of your table should be dead tuples. And you can take a snapshot in time and figure out how long it is, but you want to make this decision ahead of time. You know, how much bloat am I going to tolerate? Obviously, when my database gets significantly larger, a lot more bloat is a lot more problem. Okay. Next thing is you always want to adjust the default values to be more aggressive. Raise the cost limit. Okay, so the default is in Postgres 11 is 200. You could do or lower the cost delay. The cost delay in Postgres 11 is 20 milliseconds. I believe in Postgres 12, they've reduced that by a factor of 10 to 2 milliseconds. And then you want to lower the scale factor. All right, so decide, you know, you make that lower so it will run more frequently. So effectively, you can think of Postgres as tuned in such a way that vacuum will not be that disruptive on a small database, and I'm saying out of the box is tuned that it'll be not that disruptive on a small database, but will be very disruptive on a large database. Another thing to remember is vacuum cost limit is shared across all workers. So if you have 5 workers all performing vacuums, the cost is calculated across all of them. So generally speaking, it's better to, if you're going to either lower the vacuum cost delay or raise the cost limit, better to lower the cost delay. You'll get more benefit. But if you anticipate 5 worker processes being run at the same time, you want to consider this as well. You know, making these values a lot higher. All right. So there's some design principles you should always think about with vacuum. Okay, if possible, avoid having large update-intensive tables. Okay, so multi-terabyte tables that are going to do a lot of updates and inserts and deletes are going to invoke various vacuum operations and are going to create lots of particular tuning that you need to do. The next thing is don't spuriously add indexes. Consider what indexes you're adding carefully. Do it as a result of query tuning. Monitor them both on the primary and the standby to ensure that they're not doing. And you want to look at your statistics. How long has it been? Have I run the statistics for 6 months? Have I found any indexes? One thing that we're going to talk about in a future thing is the fill factor on a table. That'll be in the next presentation about fill factor and how that works with hot updates. Starting with Postgres 10, there's something called declarative partitioning, and it got significantly better in Postgres 11, and much more performant. And I think in Postgres 12, it's going to take yet another step forward. If you can break your large tables into smaller tables, all right, so if I have a table, if I have a trades table, if I can partition those trades by dates, that creates a lot of small tables where I have a trades by month, and I can vacuum those tables quickly and easily without disrupting other tables. And then there's less scanning that has to occur on the tables and on the indexes. So partitioning is a good way to avoid some of the pain you can experience with vacuum. The other thing is decide what your maintenance windows will be. How long will they be? Can you do can you vacuum fulls during that maintenance window? Okay, another thing that's really important in Postgres is to avoid long-running transactions. So I have a user interface that does a transaction begin, allows me to go get a cup of coffee, and then I come back 3 hours later and start working with it, and the transaction's been open that whole time. That is an opportunity to create lots and lots of bloat and lots of tuples. DDL operations, vacuum will get out of the way of DDL. So if it sees something where you're doing an alter column, vacuum will stop and will yield to those kind of things. So if you have a database where you're doing lots and lots of DDL, creating tables, altering columns, adding partitions, etc., you potentially have some issues with vacuum. So consider your DDL operations carefully when you're doing this. So things you want to monitor in the area of vacuum. One is table bloat. How bloated is the table? Are you crossing certain thresholds? The CPU usage, okay, is a vacuum consuming lots of CPU. Disk I/O rates, obviously, what's happening during vacuum. If you can monitor your vacuum for your disk I/O or things problem. Okay, one thing we didn't talk about is XID consumption. That is going to be covered in the advanced vacuum through pictures topic, where we'll talk about freezing and how XIDs are consumed. And then the time since your last analyze, and monitor long-running transactions. Do you have any transactions out there that are running for minutes or hours or days? Do you need to make a decision on those? And those are sort of your top items relative to monitoring. So in summary, vacuum kind of consists of the following principles. Understand what it is and how vacuum works. Design for those with that understanding. Monitor vacuum, what the operations are that I mentioned previously here. Monitor the things that can happen, and then tune based on the above. All right, so thank you very much. I usually do this talk with Andrew Dunstan, so you can send either one of us email. You can send info at Second Quadrant to info@secondquadrant.com. Visit our website, and we'll be happy to help you with vacuum topics or any other topics you may be interested in. So with that, I guess I will turn it over. I will allow some time for questions.
Thank you, Tom, for a great presentation. We have received quite a few questions from our audience. So I'm going to start with the first one, which is what happens when all of the dead IDs cannot fit in the work_mem?
That's a very good question. In that case, it'll do multiple passes. So it will go until it can get all the IDs in work mem, and then it will start again. So it has to take multiple passes to do it.
Okay. Next question is there a way to calculate how much space could be set free after a full vacuum?
Uh, that's also a very good question. The answer there is you have to kind of measure how much bloat is on the table, and based on how much bloat is on the table, you can run a query. And there's something called an extension called pgstat tuple that will tell you how many of the rows are dead and how much dead data there is. It'll tell you, and then based on that, you can determine what you could expect to reclaim as a result of a vacuum full. What disk space you could reclaim as a result of a vacuum full. Okay.
Uh,
Let's say, okay, so
okay.
here, what will vacuum full on a partition table, partition lock the whole table, only that particular partition. Okay, so if you do a vacuum full and you give it the name of the base table, then yes, it will lock the whole table. But remember, partitions are individual tables. So I could do a vacuum full, partition 1, and it would only lock that particular partition as opposed to the whole table. Okay, next question. Let's see.
So next question is, uh, will vacuum full on a partition table partition lock the whole table or only that one particular
Right. No, I think
partition?
I think I just answered that one. So I think we're on to the next one.
Okay. So the next
Is
one
there?
is, uh, what can be the reason when vacuum runs for a long time for one run and for another run it completes quickly for the same table?
Well, there's a lot of factors to that. The question is, what else is going on in the system? How many dead tuples are on the table? So if let's say it's been it's been 10 minutes since the last vacuum, it will be is it'll be 10 minutes since the last vacuum. How long will it take, or versus 2 months since the last vacuum? It's really a function of how many dead tuples there are and how much what are their activities going on in the on the server. So if there are a lot of analytical queries running at the time, it can be problematic.
Okay. Uh, one final question, which is there a way to stop full vacuum once started to make table available for use?
Yeah, you can effectively, if you're at the command line, when you do it, you could just stop it via a control C, but you could terminate the backend using the pgset terminate backend. I want to, let me, I don't know, I want to just research that a little bit. I'm a little less sure about that particular answer. So I want to, I'll just post that in the, when the video is recorded. The question is, what is there a safe way to stop a vacuum full once it's started? I believe the answer is yes, but I want to check something there.
Okay. So I've been told we have more time to take a few more questions. So
Okay.
uh, next one uh, is it possible to know how much time will it take to vacuum a table? What happens if we stop the vacuum process in the middle? I think that has been answered as well, right? In the last one.
Well, no, it's a little bit different. Well, to some
Okay.
extent, yes and no. I mean, there really isn't, but you can anticipate how much bloat there is on the table. And remember, vacuuming generally does not stop any other operations on the table. You can still select, insert, and delete on the table. You can't do DDL operations on the table, but generally speaking, you can do everything else. So you don't, if you can avoid it, do not stop a vacuum process.
Okay. Another question is, can auto vacuum be restricted to run only by time, that is, run on weekends or a certain time?
No, it's always based on thresholds. So auto vacuum, you can run vacuum from a cron. that's how you would make it run a certain. That's how you would do that. You'd run a vacuum process from a cron. But auto vacuum only is only configured when the database crosses thresholds. It's meant to be event-based as opposed to time-based.
Okay. Another question for you, Tom, is why does a long-running transaction increase bloat if doesn't do anything in that idle session?
Right. The issue is that there may be lots and lots of other sessions that are doing things and creating lots and lots of dead rows or whatever it may be doing, and as a result, it only will vacuum the row or reclaim the row if there are no other transactions that let's see, let's say phrase this correctly. There are no other transactions that that need access to the row. So if the transaction started a long time ago, it needs to preserve all the rows that were deleted or updated since that time. So it's not necessarily what that particular session does, it's what all the other sessions on the database do. If the database is idle across the board, it'll be fine.
Okay, so with that, we have come to the end of this session. We have received quite a few questions regarding the recording. Yes, the recording will be available in in a few hours. You will receive a notification about it. So yes, you can watch the recording later. In case you have any questions, please send them to webinar@secondquadrant.com. If you have any question related to Postgres, do get in touch and send an email to info@secondquadrant.com. As Tom said earlier in his presentation, we will be covering more topics related to vacuum later on. You can visit our website for regular updates. You can also subscribe to our newsletters, blog updates to keep up to date with Postgres news as well. So thank you so much, everyone. Thank you, Tom.
All right,
Have a
my
nice day,
pleasure,
everyone.
and look forward to seeing you all in a future webinar and potentially working with you in other capacities in part of Second Quadrant or part of the Postgres community.
Thank you. Bye-bye.